So, now let us come back to Laplace transform. So, let us return to Laplace transform. Okay, so we learned what are the what to say the what is the definition of the unilateral Laplace transform. So, now let us look at some properties, okay, like which we are going to use. Okay. The first one is transform of derivatives. So, first let us see how derivatives of functions transform when we apply the Laplace transform. So, for example, if so f of s is equal to the Laplace transform of or let me write the other way. Let us say if I take a function f of t, if the Laplace transform of f of t in the time domain is indicated by capital F of s in the complex domain, then the Laplace of df dt is going to be equal to s times f of s minus f0. Okay. So, here what is f0? f0 is nothing but f of t evaluated at t equals 0. Okay. That is the initial condition once again. Okay, that is the initial condition. Similarly, the Laplace transform of the second derivative of f, which is d squared f dt squared, is going to be s squared f of s minus s times f0 minus df dt evaluated at t equals 0. Okay, so, that is the Laplace transform of the second derivative. Okay, now we have two initial conditions, right, f and f dot. Okay. So, as far as this particular course is concerned, you know, like if we use dot over a variable, that means it is one derivative with respect to time. Okay. So, that is the notation we are going to use. Similarly, if we use two dots, it is a second derivative, okay, and so on. So, the number of dots over a variable indicates the order of the derivative, right, with respect to time. Okay. So, we see that, you know, like as we keep on going to derivatives of higher order, we are going to get as many initial condition terms, right, in the time domain, right. So, that is the first property, you know, like which we would be using. Okay. The second property is what is called as the initial value theorem. The initial value theorem essentially says that limit t tending to 0 f of t is nothing but limit s tending to infinity s times capital F of s, right. That is what is called as the initial value theorem. And there is another theorem which is called as the final value theorem. So, what is this final value theorem? Limit t tending to infinity f of t is going to be equal to limit s tending to 0 s times f of s. Okay. So, that is the final value theorem. Then the fourth property that we would be using is what is called as a complex differentiation theorem. So, what is this complex differentiation theorem? It just states that Laplace of t of f of t is going to be equal to minus d of d times f of s ds. That is like we take the derivative in the complex domain, right. That is why it is called as a complex differentiation theorem. So, then there is something called as a real integration theorem. So, what is this real integration theorem? Let us say I integrate the function f of t, let us say between 0 and t. Okay. So, what we have is that we have the result to be f of s divided by s. Okay. So, in fact, like if you use tools like MATLAB and Simulink, okay, this is the reason why we see the block s for derivative and 1 by s for integrals, right. So, if you use Simulink, you know, like this is the graphical user interfaces that we would have for a differentiator and a integral block, right. So, that is because of this Laplace transform, because when you take derivative we introduce s in the complex domain and we multiply by s, and then when we integrate we divide by s, right. So, that is why we have these blocks. Okay. And another theorem which we are going to use is multiplication by an exponential function. I am just pointing out what are the properties which are useful. This just says that Laplace of e power minus at f of t is going to be equal to capital F of s plus a. So, let us say if I multiply the function f of t by e power minus at and take the Laplace transform of the product, the complex domain wherever I have s, I just substitute s plus a. Okay. So, that is what is the what to say multiplication by exponential function, you know, like results in, right. So, typically what we have is that like we have a table of Laplace transform, okay, like I am just going to write a table of Laplace transform, you know, like I strongly suggest that you derive this table, you know, like based on the definition that we have, definition of the Laplace transform that we have written down. It is pretty straightforward. So, but let me just complete this. So, if you have the unit impulse, the Laplace of the unit impulse is 1. And if you have the unit step, the Laplace transform of the unit step is 1 by s. If you have the unit ramp, the Laplace transform of the unit ramp is 1 by s square. If you have an exponential function e power minus at, the Laplace transform of the exponential function is 1 by s plus a. So, if you have cos omega t, the Laplace transform of cos omega t is s divided by s square plus omega square. If you have sin omega t, Laplace transform is going to be omega divided by s square plus omega square, right. So, that is what we are going to have. Okay. So, this is just a preliminary table of Laplace transform. Of course, we can add more what to say functions, okay, as we go along, but I have just listed whatever we are going to use very frequently. So, just to demonstrate a few theorems, right. So, even if I want to demonstrate this, suppose let us say let f of t be cos omega t, then what will happen is that like the Laplace of e power minus at cos omega t is going to be f of s plus a, right, that is what it means. So, the Laplace of cos omega t is s divided by s squared plus omega squared. So, what this theorem tells me is that wherever you have s, substitute s plus a. So, I am going to substitute s plus a wherever we have s. So, the Laplace transform is going to be s plus a divided by s plus a whole square plus omega square, right. So, that is what we are going to have. Similarly, we have the Laplace of e power minus at sin omega t to be equal to omega divided by s plus a whole square plus omega square, right. So, that is what we are going to have. Okay. So, we would see that, you know, like at we will keep on adding to these properties and let us say some more Laplace transform as we go further in this course, but from a very what to say big picture level, what we are going to do is that like we are just going to apply this Laplace transform operator on linear ODEs with constant coefficients. Okay. So, and how do we get these linear ODEs with constant coefficients? As we discussed, the typical mathematical models using the modeling approach that we use for the class of systems that we are considering in this particular course take the form of linear ODEs with constant coefficients, right. So, that is our rationale, right. So, we use a Laplace transform and then like convert them into algebraic equations, which we can then what to say analyze. Okay, but there is a catch here, right? What is the catch? In the if when we are dealing with linear ODEs and complex when we are dealing with linear ODEs with constant coefficients, we are in the time domain, but that goes to the S domain, right? So when we apply the Laplace transform, so we convert the problem into a problem in the complex domain, right? And so here we will shortly see that, you know, like we need to have a basic understanding of polynomials to essentially work with the algebraic equations that we get in the S domain, right? So that's also something which we will look at as we go along. Okay, so a couple of more concepts in Laplace transform that we would recap is that how to take the inverse Laplace transform. Alright, so how do we take the inverse Laplace transform, right? So suppose let us say I am given a Laplace transform function which is f of s is 1 by s squared plus 3s plus 2. Let us say I have this Laplace transform, right? So then what happens? What we need to do is that, like, we need to do what is called as partial fraction expansion and then like take the inverse Laplace transform, right? So we see whether we can factorize the denominator polynomial. In this case I can factorize s squared plus 3s plus 2 as s plus 1 times s plus 2, and this can be factorized as a divided by s plus 1 plus b divided by s plus 2. Okay, so that is what we have. Okay. So then a and b are what are called the residues of the two factors. Okay. So how do we find a and b? Of course we can use LCM and then like we can essentially equate the coefficients of the numerator polynomial on both sides and then we can solve. There is also another method to solve for a and b which I will just teach you. If they are that is in this case it is going to be pretty straightforward because they repeat only once. So that is, of course they appear only once, okay, they do not repeat. Okay. So if I want to find a, what I do is that I multiply both sides by the factor s plus 1, okay, which is in the denominator. So this implies that the left hand side will become 1 divided by s plus 2, the right hand side will just become a, and then I will have b times s plus 1 divided by s plus 2. So what will happen to this? Now this equation is valid for any value of s, right? So what I do is that I substitute the root of the factor that I have multiplied with. Okay, so what is the root of s plus 1? A root of a polynomial is indicates those values of s at which the polynomial is 0, right? So that's essentially the meaning of the word root, right? So the root of s plus 1 is equal to the root of s plus 1 is going to be s equals minus 1, right? So I substitute s equals minus 1, the left hand side becomes 1, the right hand side I have a, and b times s plus 1, that term vanishes, right, because s plus 1 at s equals minus 1 is 0. So that b term vanishes. So we see that we very easily get the value of a. Similarly, I hope now you get the point, right? So if I want to find b, I multiply both sides by s plus 2, we are left with 1 divided by s plus 1 on the left hand side, then I will have a times s plus 2 divided by s plus 1 plus b, and of course now I need to substitute the root of s plus 2, that is going to be s equals minus 2. So what I am going to get is minus 1 on the left hand side, a times s plus 2 vanishes at s equals minus 2. So I am just going to be left with b. Okay. So as a result, what is going to happen is that this partial fraction expansion is going to be 1 divided by s plus 1 minus 1 divided by s plus 2. Now once we have broken down into blocks that we can easily process, we look at the table of Laplace transform, right? Immediately we can see that if I look at the table of Laplace transform, the Laplace inverse of 1 by s plus 1 I can write as e power minus t, and 1 by s plus 2 I can write as e power minus 2t. Okay, so that is the way we will do the inverse Laplace transform. Okay, so this is what is called as a partial fraction expansion. Okay, so these quantities A and B are what are called the residues, right, of the partial fraction expansion process. And one important application of Laplace transform for us, okay, is to solve initial value problems. Okay, so that's essentially one important application from our perspective, from our course perspective. Because why? Because we are going to deal with models that take the form of linear ordinary differential equations with constant coefficients. So let me consider an example. Let's say I have a system whose governing equation is given by, let's say, y double dot plus 5y dot plus 6yt equals u of t. Okay, let's say like y 0 is 0, y dot 0 is 0, right. So let me say that like consider a system whose governing equation is okay, is the following. So so what we are doing here is that, let's say we want to find its unit step response, right. So let us say that is find y of t for u of t equals 1, right. So that is what we want to do. So as a solution, what we do is that, like we take Laplace transform on both sides, of this particular equation. So what happens? So for y double dot, we will get s squared times y of s minus sy0 minus y dot 0, right. That is the Laplace transform of the second derivative. Then we will get 5 times for y dot, we will get sy of s minus y of 0 plus 6y of t, we will get 6 times y of s, and that is going to be equal to u of s, right. So yeah. So if u of t is 1, this implies that u of s is 1 by s, right. So we know that the Laplace transform is of 1 is 1 by s, right. So that's something which we already know, right. So given this, wait a minute. So let's process this. So what we are going to get is the following. So if I group terms involving y of s, let us say I will have s squared plus 5s plus 6 y of s, and then I will have minus s plus 5 y0 minus y dot 0, that is going to be equal to 1 by s, right, because u of s is 1 by s. So this will imply that y of s is going to be equal to s plus 5 y0 plus y dot 0 divided by s square plus 5s plus 6 plus, of course, for the time being, let me go back and keep this as u of s. Okay, I will tell you why. Okay, so let us say we keep it as u of s. So I have s squared, sorry, u of s divided by s squared plus 5s plus 6, right. That is what will happen. So immediately we see that this is the response due to initial conditions, right. I am repeating it again. So this is what is called as a free response, right. So this is the, because y0 and y dot 0 are the initial conditions, like, of course I have given the values to be 0, that is a different matter, but I am doing a general derivation where this is the component of the output due to the free initial conditions, what we call as free response. This is the output due to the input that we provide, right, due to input provided. So that is called as a forced response. Okay. So now we substitute okay. Now we are given y0 is 0, y dot 0 is 0, right. This implies that y of s just becomes, and of course we are also given u of s is 1 by s, right. So, that is also something. So, if you substitute, the free response term vanishes, right, because in this particular problem we have just considered the initial conditions to be 0. So, the free response term vanishes. So, the forced response term is what we are left with. So, we will just get 1 divided by s times phi s squared plus phi s plus 6. This comes out as, if I factorize phi s squared plus phi s plus 6, I can rewrite it as s plus 2 times s plus 3. So, the denominator becomes 1 divided by s times s plus 2 times s plus 3. So, this can be rewritten as a by s plus b by s plus 2 plus c by s plus 3. Okay, once again, if I use the method that we discussed previously, let me do it one more time. So, if I want to find a, I multiply by the multiply by the factor involved in the denominator of a, which is s. So, the left hand side becomes 1 divided by s plus 2 times s plus 3, that is going to be a plus bs divided by s plus 2 plus cs divided by s plus 3, and here I substitute the root of s, which is s equals 0, right. So, consequently, I will get 1 by 6 on the left hand side and just a, right. Similarly, if I want to find b, I multiply by the factor the denominator of b, which is s plus 2. So, I will get 1 divided by s times s plus 3, that is going to be equal to a times s plus 2 divided by s plus b plus c times s plus 2 divided by s plus 3. And here I substitute the root of s plus 2, which is s equals minus 2. So, I am going to get minus 1 by 2, right. I hope I am doing it correctly. So, if I substitute s equals minus 2, I get minus 2 times minus 2 plus 3, which is plus 1. So, I will get minus 1 by 2, and that is going to be equal to b, right, because the a and c term will vanish. So, similarly, if I want to find c, what I will do is that I will essentially multiply both sides by s plus 3, the left hand side becomes 1 divided by s times s plus 2, that is going to be a times s plus 3 divided by s plus b times s plus 3 divided by s plus 2 plus c. Now, we substitute the root of s equals s plus 3, and that is equal to s equals minus 3. So, we are going to get 1 divided by minus 3. So, times minus 3 plus 2, that is minus 1. So, 1 by 3, that is going to be equal to c, right. So, if I substitute back here, so I am going to get 1 by 6 s minus 1 by 2 times s plus 2 and my plus 1 by 3 times s plus 3, right. Okay, so I think that is what we will have. So, this will give me y of t to be equal to, I hope I did it correctly, I am going to minus 1 by 2 and here I am going to get plus 1 by 3, yeah. So, if I take the inverse Laplace transform just by looking at the table of Laplace transform, 1 by 6s will give me 1 by 6, right, and minus 1 by 2 times s plus 2 will just give me minus 1 by 2 e power minus 2t, and 1 by 3 s plus 3 will give me 1 by 3 e power minus 3t, right. So, that is what I will have. Okay, so, we see that the process of calculating the solution, okay, to the ordinary differential equation, okay, like becomes pretty simple, right, because we are considering converting the ODE into an algebraic equation and then we process that, right. So, that is how we are going to use Laplace transform for our advantage, right. So, to once again give a big picture perspective, we are dealing with SISO LTA causal systems which are going to be modeled using spatially homogeneous dynamic continuous time deterministic models that will typically result in linear ODEs with constant coefficients. And once we get linear ODEs with constant coefficients, we are going to use Laplace transform and convert them into algebraic equations and then we calculate the output or response of the system to various standard inputs and we analyze them. Okay, so that's the big picture, the viewpoint. That's why we have studied all the concepts till now, right? So to just set up the foundations, right? So following this, we will we look at we'll go further. We'll see how we represent the system, and then we see what are called as transfer functions, and then how do we use transfer functions in our analysis. Okay, so we are going to look at the big picture viewpoint following this, right? But I'm just going to leave you with a few problems that you can do as exercises. Okay, so that we become familiar with the inverse Laplace transform. So once again, I'm sure all of us would have learnt it in an engineering mathematics course. This is just to help you with recapping all those concepts, right? So please go back and let's say find the inverse Laplace transform of the following functions. 1 divided by s squared plus 2s plus 2, let's say 1 divided by s squared plus 2s plus 1, right? 1 divided by s squared plus s. I'm just giving simple examples. Okay, so 1 divided by s squared plus 1. Okay, and let's say 1 divided by or let me say s divided by s squared plus 1 whole squared. Okay, let's make it interesting. So and then let's say 1 divided by s squared minus s, sorry, plus s minus 2. Okay, let's say please go back and work out the inverse Laplace transform of these functions. Okay, and then we would continue from here. Okay, thank you.